Hello everybody! In this video, torque wrenches. Again, different types, how do they work? How to use them? Pros and cons of different kinds. There are many types and variations of torque wrenches, and it is hard to present all possible options in a short video. In general, I would divide them into split beam type, compression spring loaded, digital, and hydraulic. Obviously, I don't have torque wrenches with all possible mechanisms, but I will present what I have and present concepts of the wrenches that I don't have. Let's get started with this simple split beam type. It has this main beam with the handle at the end. Permanently attached to it is the scale with torque values marked on it. Here is the head that holds a socket, and this tiny beam parallel to the main one. It ends with the pointer over the scale. Using Hooke's law, we can measure the torque value applied to the fastener. When we apply force to the handle, the main beam deflects. The degree of deflection is proportional to the torque value applied to the nut or the bolt. The main beam deflects with the scale. The tiny beam stays put, pointing to the torque value marked on the scale. Simple torque wrench that works clockwise and counterclockwise. The problem with it is the fact that we must observe the pointer perpendicularly to the scale to get the right reading. We cannot preset this wrench in any way to let us know when the desired torque value is achieved. Based on the same principle of two beams works this split beam torque wrench. Inside of it we have two beams. Long one that is deflecting when we apply force to the handle, and this short one which is stationary. Here we have this small latch which breaks the bond between long and short beams when the main beam deflects. The main beam can be set in relation to the short one with this screw here, depending on desired torque. This screw pre-deflects the main beam since it is set up against the body of the wrench. It also runs gears, which works as a gauge. Here we have the locking mechanism which prevents free movement of the set screw. This way we can lock in the desired torque value on the wrench. To calibrate the wrench, this insert must be screwed in or out to adjust the point when the latch let go. This wrench can be used only in clockwise direction. We can hear when the latch mechanism let go at the set torque value. The other advantage of this kind of wrench is that we can leave it for storage set at any value, since there is no spring inside that can throw out calibration over time. Another kind of torque wrenches is the click type. Those are probably the most common torque wrenches used by automotive mechanics and do-it-yourselfers. Inside we usually have a kind of cube or rollers which at predetermined points break the linear alignment between parts of the wrench. The breaking point is determined by this spring, which tension can be adjusted, setting desired torque value that must be delivered to the bolt or the nut. Calibration of this wrench can be done by setting pre-tension of the spring by screwing in or out this big screw that goes into the wrench handle. Small screw locks the handle, preventing it from turning. The head with this short lever pivots at this point on this pin when desired torque is achieved at the bolt or the nut, making click sound and letting us know that the operator should stop pulling the handle. Some models of this type torque wrenches can work both directions, but this will be specified in the owner's manual. This specific one works one way only. Click-type torque wrenches must be set to the lowest torque value for storage to avoid deformation of the inside spring that will mess up calibration. So many times I saw people who do their wheels changes between seasons where they set the wrench and keep it at this setting for years. Don't do it. To set the desired torque value on the wrench, we either pull down the sleeve, unlock the handle by loosening the small screw at the end, or turn the lock ring and then turn the handle. And after setting the torque on the scale, we must lock the handle. Usually this type of torque wrenches have two scales, one in foot-pound or inch-pound and in Newton meters. This type can be set to the mark. This one can be set anywhere between. Because those wrenches have two different torque units on the main scale, they also have two scales on the handle to set the wrench. Let's see how we set the wrench. This one is set now to the lowest mark of 20 foot-pounds. 0 point on the handle set to the main bar on the wrench scale. Foot-pounds. 20 and 0 gives us exactly 20 foot-pounds. When I turn the handle, it climbs on the numbers. 26. Even though there is a mark between numbers, we can only set it at full number. 30 foot-pounds. 33. Let's set it in Newton meters. Lowest point 33.9 Newton meters. Turning the handle, now I will look at the lower numbers on the handle. Let's say I need 85 Newton meters on the wrench. Here I have 88.1 and here is 74.6. I turn the handle to the 74.6 point. Lower scale at 0. Now I turn it to 9.45. It gives me 74.6 plus 9.45, which is 84.05 Newton meters. I turn it one more notch, and here I have 74.6 plus 10.8. 85.4 Newton meters is the closest I can get to 85 on this wrench. This type of wrench I can set between the marks, but there is one problem with it. The scale on the handle is only for the foot-pounds scale. To set this wrench in Newton meters, we must multiply the number on the handle scale by 1.36. Got European spec torque? Have fun with this wrench. Oh, and a calculator. This type of torque wrenches let us know when the set torque is delivered to the fastener by breaking up and click sound. The force should be applied perpendicular to the wrench holding it only by the handle. We must pull slowly and stop pulling immediately when the wrench breaks up. The wrench is designed to break at 2 to 3 degrees. After that threshold, additional torque will be applied if we don't stop pulling. There are types of wrenches free from this limitation that I will talk about later in this video. Another type of torque wrenches is digital torque wrench. Those are equipped with strain gauges. When they experience mechanical deformation, their electrical resistance changes, and this can be interpreted by electronics and displayed as torque. It will let you know buzzing or with LED light when the desired torque is reached. The operator can choose from many units of measurements and set desired torque. Some digital wrenches have an angle function. Sometimes we need to apply torque in stages and then additional rotation angle. Without a digital wrench with such a function, we would use a regular torque wrench for the first stage and then this kind of device, but this time with a regular wrench. And I mean not a torque wrench, but a regular wrench. Sometimes we can use an extension with our torque wrench to extend its capacity or just to get to hard-to-reach bolts or nuts. When we set the extension at 90 degrees to the length of the wrench, the set torque value will not change. What is set on the wrench will be delivered to the fastener. Let's do a test. Here I have an extension 3 3/4 inches in length. Each wrench in this test is set to 40 foot-pounds. Keep in mind that each torque wrench tested here is accurate within plus and minus 4%. Therefore, we are looking for a certain range they will signal achieved torque. The tester is accurate within plus and minus 1%. As you can see, whatever type of torque wrench we use, when the extension is set at 90 degrees, the torque delivered to the bolt or the nut is the same as set on the wrench. It is a different story when we use extensions to elongate the wrench. In each case, we can calculate the torque value delivered to the fastener using this formula. Our D is the torque value at the bolt or the nut. N is the torque value set on the wrench. L is the distance between the center of the wrench head and the middle point on the handle. E is the extension length measured from the center of the wrench head to the fastener center. This split beam torque wrench has 15 3/4 inches. According to the formula, we expect 49.5 foot-pounds. I don't convert inches to feet because proportions will be the same. This click-type torque wrench has 17.5 inches from the head to the middle of the handle. Keep in mind that this torque wrench length changes when we turn the handle to set the torque. According to the formula, we expect 48.4 foot-pounds on the fastener. The digital torque wrench 14 inches. And the formula gives us 50.7 foot-pounds. What will happen if we apply force not to the handle? There is controversy about this. Some people claim that no matter where you hold it, it will click at the set value. I did a video about this subject with an explanation based on click-type torque wrench. But they still insist that discrepancy comes from the fact that I had to apply greater force holding the torque wrench closer to the fastener, and couldn't stop my hand in time over-torquing the fastener. Well, this type torque wrench clicks before I reach 40 foot-pounds. Let's repeat the experiment with click-type torque wrench. This time I set it at 63 foot-pounds. At the handle. Holding it closer to the lug nut. Even before clicking, it goes beyond 63 foot-pounds. So the problem is not about stopping my hand at the right moment. Let's try it the other way. Now the digital torque wrench held closer. I was not able to do the test with the simplest torque wrench since the head was not ratcheting style. Couldn't set it at 90 degrees or straight. When we use an extension to reach the fastener, it will not change the torque value, as long as we can hold the wrench in the axis of the fastener. This time we are allowed to use the second hand, but only to support the wrench head. It will affect the outcome by a small degree. The other hand is also allowed when we must apply more force, but only overlapping the first with the second. The force must be applied only to the handle. Every single torque wrench owner's manual says so. In the second part of this video, I will talk about other types of torque wrenches that I don't have. Recently, I came across this type of torque wrench. Those are small, split beam types. This one works between 10 and 20 Newton meters. This one even smaller, from 3 to 10 Newton meters. Another one based on Hooke's law is this deflection type torque wrench. Here we have the main beam with the handle at the end. And this short beam bent at the end. When we apply force to the handle, the main beam is bending. When it bends enough so this wedge comes into contact with this trigger, the spin is released, making a clicking sound and letting us know that the desired torque value is achieved and we should stop pulling. Here we have the drive square for a socket, and this is the point where the beams are fixed together. This torque wrench works only in clockwise direction. How can we set it to the desired torque value? We can set the wrench by moving this wedge. This screw holds the wedge to the slot permanently attached to the wrench. By loosening it, we can slide the wedge. This mark moves with the wedge over the scale pointing to the torque value. Here we have a set screw to calibrate the wrench by moving in and out the mark. Depending on the set torque on the wrench, the wedge is closer or farther from the trigger. When the main beam deflects enough, press on the trigger and the trigger releases the side pin, which makes a clickety-clack sound. Another one split beam type, even though it is called a dial torque wrench, is this one. the handle, the dial, the drive square. Here is the side view. The handle, the dial is here, and here we have the cover for the wrench mechanism. Inside we have two beams. The main one is attached to the wrench here. And it ends with the drive square. Here the small beam is attached to the main one. And it ends at the dial pointer mechanism. When we apply force to the handle, the main beam deflects. The small one doesn't bend, but it counteracts the movement of the main beam and reacts with the needle mechanism. Here is a close-up picture of the dial mechanism with the needle return spring and the slot used for calibration of the wrench. Calibration is done by moving this bent rod inside the slot. Another torque wrench that looks similar to the previous one is this dial type torque wrench. But it works differently. Here we have the handle, drive squares, and here it looks like the wrench consists of two parts. Inside, the drive square here, and it is set on this moving part of the wrench. The handle is attached to the wrench body, and this part is permanent on the wrench. This is the pin that holds the moving part to the rest of the wrench. Here is the spring, and we can regulate its tension when calibrating the wrench. When the force is applied to the handle, we compress the spring. Then, this part is moving. This pin moves with the moving section and it's turning the cogwheel. The cogwheel turns the axis with the needle attached to it. The needle points to the torque value applied to the fastener. Looking at it again, we can see the moving section of the wrench. This pin that holds both parts. Spring tension screw. The pin that moves the cogwheel. Another concept of torque wrench is this sliding torque wrench. This kind will not allow for over-torquing the bolt or the nut. Inside the head, we have a cam-type mechanism fixed to the drive square. Here is a ball. Spring. This bolt regulates the spring tension. When the desired torque value is achieved, the spring compresses to the point that it allows the ball to slip over the cam. No matter how much force we apply to the wrench handle, we cannot over-torque the fastener. Another torque wrench is this brake-back type torque wrench. This one is designed in a way that delivering a high torque value of up to 800 or even 1000 Newton meters, you will not break your back. Just kidding. This one is a beast. Long one. When we apply force to the handle and desired torque value is reached, it breaks in the middle at 18 degrees angle. So it is not 2 to 3 degrees like before, but 18. This gives us more room to stop our hand and prevent over-torquing. To set up the wrench, we must use a special crank provided with the wrench and turn this bolt at the handle. The spring inside the wrench is a strong one. Here is the closer view. There is a latch mechanism inside. Inside here we have the spring. This wrench is long and consists of two parts joined here. Can be disconnected and stored in a case in two pieces. The last one presented here is a hydraulic wrench. Here is the main part. Inside we have this cam attached at this end to this hydraulic cylinder. The oil pressure applied to the cylinder determines the torque value applied to the fastener. Here we have an open type socket which goes on the bolt or the nut. This white ring is a gear wheel. Here we have a wedge that can move inside the cam and has teeth to mesh with the gear wheel. When the oil pressure pushes the piston inside the hydraulic cylinder, the cam moves. The wedge mesh gears with the gear wheel and turns the ring with the fastener inside. When the piston retracts, the wedge let go by moving upward into this void. There is a spring inside. The cam returns to the initial position without turning the fastener back. This wrench must be set against something like a neighboring bolt or nut or another solid part. It is easy, since this type of wrench is used to put together pipeline flanges, vessel covers, or wheels of big machines. Obviously, there are many more types of torque wrenches, mechanisms, and variations. Hard to cover everything in one video. Till next time.